In this video, we're going to talk about structural factors, that is, things we can look at in the structure of molecules that affect how strong acids are. So when we're done with this, you should be able to at least predict the relative strength of some acids, even if you can't predict the absolute strength of an acid. All right, so let's consider an acid, right? Some generic acid, HA, where the atom A is an atom, represents atoms in the same period, right? So carbon, nitrogen, oxygen, fluorine, right? Go across the same period or row of the periodic table, right? Sulfur and chlorine are in the same period or row in the periodic table, right? And so what we can do is look at the typical pKa values for bonds of this type. So the pKa, for a typical sp3 carbon-hydrogen bond is in the range of 60, right? That means that the Ka is in the range of 10 to the minus 60, right? And the smaller the number, the weaker the acid, right? So the pKa for a typical carbon-hydrogen bond is in the range of 60. A typical nitrogen-hydrogen bond is in the range of 36. A typical hydrogen-oxygen bond is in the range of 15. And fluorine-hydrogen bond is in the range of 3.2. Okay? So, as we can see, as we go this way, right, across a period, the acid gets stronger, right? And let's see if the pattern holds when we move down a period, right? If we consider, right, a typical hydrogen-sulfur bond, the pKa is approximately 7, and chlorine-hydrogen bond, pKa is minus 7, right? Which means, right, it's getting smaller. This is one of our strong acids here when we get to pKa's that are negative. That means our Ka is 10 to the plus 7 or 10 million, right? That's going very close to completion when we put hydrogen chloride in water. And the trend here goes, right, as we go this direction, we've got increasing electronegativity of the atom A that the hydrogen is attached to. The greater the electronegativity, right, if we've got A and we've got this unshared pair with a bond to the hydrogen, right, the greater the electronegativity, the closer these electrons are going to be held to A, and the more likely then the hydrogen ion is going to be attracted to something else that has electrons, and so it is likely then to leave, right? If there's something else that can provide it electrons better than A can, right? So we can look directly at the electronegativity, right? Electronegativity increases as we move left to right, and as we go left to right in any period, a hydrogen-nitrogen bond or a hydrogen-oxygen bond, right? A hydrogen-A bond, right, gets more acidic as we move left to right in any period, okay? So now let's consider the other direction, right? Let's look at acids, right, as we compare atoms in the same group, right, or column on the periodic chart, right? Well, if we do that, we notice that our pKa's get smaller. That is, our acids are getting stronger as we go down. Right? Our acids are getting stronger, right? Same thing's true in this column. Well, this is, so something different must be going on because we know that electronegativity increases in this direction, right? Electronegativity increases in that direction and that direction, right? So fluorine, is the most electronegative. So when we're dealing with a group, electronegativity must not be the important factor, right? There has to be something else, right? And that something else can be discussed in different ways, but I'm going to discuss it in terms of the atomic size of A, and especially of its anion A minus, right? So we're going to talk about the trend in size of the atom to which the hydrogen is attached. Okay, so let's look at some properties here of our different hydrogen halides to illustrate this, right? We said that the hydrogen halide as acids get stronger as we go down. Now, we may still consider in water, right? We may still consider all of these strong acids in water, but if we put them in non-aqueous environments, hydrogen iodide is a stronger acid than hydrogen bromide, and hydrogen bromide is a stronger acid than hydrogen chloride. It's just, even if in water they act the same, in other mediums we can see the difference. Okay, so if we look at this, right, if we look at the radius of the anion, and this is in picometers, right? So for the fluoride ion, it's right? So the fluoride ion has a radius of 136 picometers. The chloride ion, 181. The bromide ion, 195. And the iodide ion, 216, right? And so that affects the hydrogen to other atom bond distance. And so if we go, right, Coulomb's law, right, that the force of attraction between charged particles is equal to some constant times the charge on one particle times the charge on the other particle divided by the radius between them, the distance between them squared, right? Increasing the distance between them reduces the attraction between them. So the attraction between the hydrogen ion and the iodide ion, because the distance is greater, is less than the force of attraction between the hydrogen ion and the fluoride ion, right? So there's one argument from Coulomb's law that the force of attraction between those ions gets less as the size of this ion gets bigger, okay? So there's one argument for why the hydrogen iodide, bigger atoms attached to hydrogen make stronger acids than smaller atoms attached to hydrogen. Right? So our next argument is going to be based on volume, right? So if we use those radii to calculate relative volumes, we get a relative volume for fluorine, or the fluoride ion, is 1.05, for chlorine 2.48. These are in cubic picometers. Take these numbers times 10 to the minus 26. I think you get the right answer. 3.11 and 4.22, right? So, bigger radius, bigger volume. That's not the real issue. There's an issue called charge. I can write today, right? charge divided by volume we call charge density, right? So all of these ions have the same charge, right? One electronic charge, right? An excess of one electron, but that charge is distributed in very different volumes. So if we look at their relative charge densities, we get a charge density for the fluoride ion of 1.52, a charge density for the chloride ion of 0.65, a charge density for bromine of 0.52, and a charge density for the iodide ion of 0.38, right? And so lower charge densities lead to more stable ions, right? And so that lower charge density, right, makes the iodide ion as a conjugate base more stable than the fluoride ion. And so this is another factor we can look at, right? The more stable our conjugate base, often the better the acid, okay? So with the hydrogen, fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, right, we can look, they get stronger as we go down because of a combination of this distance factor and the charge density factor, right? Those are two things that contribute to the acid getting stronger as we move down the group. Right? So if we go back to our original slide, right, we see that trend, right, in strengthening acid as we go down. And so we go, let's confirm by going one left. If we look at oxygen, right, which is our second most electronegative element, right, pKa of 15, sulfur hydrogen bond, pKa of 7, right, that is a stronger acid by a factor of about, right, 10 to the 8th. Okay? So our trend holds. So as we go down in a group, the acid gets stronger as a result of those two factors we just talked about. All right, so we said one of the things that can make an acid stronger if we can make its conjugate base more stable. So let's consider these two molecules, right? We've got ethanol and we've got acetic acid. Now, there's a big hint there in the name, which is going to be the stronger acid. But with ethanol, we've got a hydrogen-oxygen bond, right? We've already encountered that. We know the pKa of something like that is in the range of 15, right? We've already encountered acetic acid, and things like that have pKa's in the range of 5, right? So why is acetic acid with a hydrogen-oxygen bond so much stronger as an acid than ethanol with a hydrogen-oxygen bond, right? Well, if we look at their conjugate, and I've tried to represent that here, right, with the arrow. We got a smaller forward arrow and a bigger backward arrow, saying this one doesn't go as far as this one does. So how do we explain that? Well, with this one, this oxygen is carrying all of that negative charge all by itself. But with acetic acid, right, we have an alternate resonance structure, right? If a pair of electrons here falls down and one of these pairs of electrons moves up, we can get an alternate resonance form of the molecule. Up, right, where now this oxygen has the single bond, and the negative charge. And this oxygen has the double bond, right? And so the negative charge is shared between two molecules, right? Let's go this way, right? It's shared between this atom and this atom, okay? I misspoke. It's not two molecules, it's two atoms, right? And so since the negative charge is shared between two atoms, that makes the charge density less on each atom, and therefore the overall base is more stable, right? So in this case, we've got acetic acid being a stronger acid than ethanol because we have more ways, we have resonance stabilization of the conjugate base. The fact that there are two resonance forms that allows two atoms to share the negative charge makes the conjugate base more stable, which makes the acid stronger. So let's consider the same argument, right? If we're considering sulfuric acid, which we said is a strong acid, right? It dissociates completely. And phosphoric acid, which we said was moderately strong, but not completely strong. It does set up an equilibrium in aqueous solution, right? The equilibrium may favor this side, but there's still some undissociated acid around, right? Novice students sometimes think that phosphoric acid, because it has 3 acidic hydrogens, should be stronger than sulfuric acid, but it's not. And we can make the same kind of resonance argument, right? So let's consider the product, the conjugate base anion of phosphoric acid, the dihydrogen phosphate ion. If we consider that same kind of resonance, we can drop a pair of electrons there, which is going to release a pair of electrons there. But we can only do that once, and so our charge is only shared between these two oxygen atoms. But with sulfur, we can go up, right? We can go this way and this way, get that oxygen involved, or we can go this way and this way and get that oxygen involved. So with sulfuric acid, the negative charge is shared among 3 atoms, making the conjugate base anion, the hydrogen sulfate ion, more stable than the dihydrogen phosphate ion. And if the conjugate base anion is more stable, then the acid is stronger. So here we have another example where resonance stabilization of the product anion is the important feature. The product conjugate base anion. Okay? So we always look for that as a factor in determining relative strengths of two potential acids. Another factor that affects the strength of a group as an acid is the proximity, or how close other electronegative atoms are that aren't directly attached. Now note, in this case, each of our acidic hydrogens is attached to an oxygen in the same carboxyl group, right? So we've got the same resonance stabilization in each case of our product anion. But we've got different atoms attached here, right? Away from where the hydrogen is, right? But we know that, right, if we're looking at electronegativity, right, that electronegativity increases in this direction, right? So fluorine is the most electronegative atom there. And so if we look at relative acid strengths by looking at pKa's, right? The pKa of acetic acid is 4.76. of bromoacetic acid is 2.86. It got stronger, right? Chloroacetic acid, 2.81, got even a little stronger. Fluoroacetic acid, 2.66, got even a little stronger than that, right? So when we have atoms away from where the hydrogen is attached, right, increasing electronegativity seems to make the acid stronger. And that's because of something called the inductive effect. Right? We know that that fluoride ion is going to pull electrons that way, right? Or the fluorine atom is going to pull electrons that way. That's how we define electronegativity. But what happens is, if that carbon is going to have some of its electron density pulled away, it's going to pull a little harder on that carbon. And that carbon is going to resist a little more when that oxygen tries to pull electrons away from it. And that's going to pull, that oxygen then is going to pull a little harder on those electrons, meaning that the hydrogen is more likely to go off with some other base that will share electrons with it, right? So the greater the electronegativity of a group away from the acidic hydrogen, the greater the inductive effect, and therefore the stronger the acid. Right? Right? So let's consider the inductive effect when we look at what happens when, not only do we add an electronegative group, which should make that acid stronger, but what happens as that electronegative group gets farther and farther away from where the acidic hydrogen is in the structure. And so if we look at this and look at the relative pKa's, for this acid, pentanoic acid, the pKa is 4.81. We add a bromine in the second position, and as we expect, it gets stronger at 2.97. But watch what happens as the bromine gets farther and farther away. 4.01 gets a little weaker. 4.51, it gets even weaker. And 4.71 when we get it, 1, 2, 3, 4, 5, 6 atoms away from the acidic hydrogen. So the farther away that electronegative atom is from the acidic hydrogen, the less effect it has on the strength of the acid, because the inductive effect gets diluted over the length of the molecule. So there are some factors we can use. If we've got two structures, even if we don't know the real strengths, even if we don't know the Ka, we should be able to look at two structures of similar molecules and predict this one will be a stronger acid, this other one will be the weaker acid. So we will need to be able to do comparisons like that.